What do you mean no?
Okay, no.
Why no? Perché no?
You can use as a laser pointer, but not as
Ah,
Vedi, c'è
ok.
il topo luminoso.
Ok. Il topo. Oh, si chiama topo luminoso.
È un gatto? Tiene il suo
Luminoso.
gatto?
Ah, ah.
Okay.
Ah.
So whenever you are no.
Yes.
It works. See?
Perfect.
Very good. Whenever you are ready, we
Thank
are
you.
ready for you.
Okay. So good afternoon, everyone. In the spirit of the school, my name is Hugo. I'm from Universidade Federal de Viçosa. So in the spirit of the school, I'm going to be presenting a little bit of algorithms and methods to simulate contagion on higher order networks. I don't think I need to spend a lot of time in motivations as to why higher order structures are important. We've cited works in neuroscience, ecology, and Guilherme, Silvio, and Mariana spoke about contagion dynamics as well. In this example, could be a virus, could be a pathogen. They can be represented by higher order networks. And there are also the social contagion networks, as Stefano said. If you were in a room with people that are all using iPhones, maybe you're motivated to start using iPhones by yourself because, well, since everybody's doing, you start doing as well. Lots of social experiments that base this assumption. So I'm going to be talking about contagion dynamics. That's what's interesting, since we have mentioned before in previous presentations. But I'm just going to remind you guys that we usually use in contagion dynamics like an SIRS or SIR. What I mean are compartmental models for contagion, meaning that you divide the population into states of an infection. Susceptible, infected, recover, you can have exposed, you can have vaccinated, anything you want you can simulate. And in this case, just to give an example of how it is the contagion dynamics in higher order networks is like this. You have susceptible, infected, and removed, and the spreading rate, the spreading events are like this. You can have a susceptible individual being infected by infected individuals. You can have infected individuals healing, becoming immune, and then you can have infected individuals, recovered or immune individuals losing their immunity, all of them at separate rates, alpha, gamma, beta, and they are all Poisson processes. Okay? Where is higher order here? Well, higher order comes in this place when you are talking about infections. Now, infections are not only something that can be spread pairwise, you come into contact with one person, but it can be a hyper edge where lots of people infect somebody else by this contact here given by a rate beta 2, meaning that's an infection of a second order hyper edge, or it can be generalized to third order, fourth order, and so on. Now, this new version, this new generalization of contagion dynamics into higher orders, they bring about several degrees of complexity. You can have networks that are now heterogeneous, not only on degree, but also on the order, right? You can have small groups, big groups, lots of groups, and that's a new degree of complexity. You now have to define rates for all spreading orders for different pairwise trios, quartets, and so on. More complexity. And also, as Guilherme told us, that the infection might not need everybody to have an iPhone for one person to adopt an iPhone as well. It can be more realistic if the spreading happens if a critical mass of a hyperedge has adopted a behavior, then other people start adopting as well, or start spreading a rumor or things like that. So all of these are new degrees of complexity that leads to amazing new phenomena like discontinuous transitions, hysteresis, multistability, and so on. So it's an interesting field, an interesting new aspects to the field that we are going to talk about how to simulate them. But about simulating them, there's a little bit of do's and don'ts, right? This is a don't. This is like a good recommendation. This paper is really good. It talks about the limitations of discrete time approaches when you are simulating contagion dynamics. And the thing is, discrete time is, okay, it's easier to implement, but it's not exactly correct. You remember that I said that infection is a Poisson process with different rates, and that adopts a form like this, an exponential distribution for the probability of someone to be infected after a specific time t. What the discrete time approximation does is that it considers the first expansion of this exponential only the first term, so it's linear. This is not right. This is unprecise for the simulations. You can see here, you can refer to the paper for a bigger discussion, but you can see here that the simulations, they become unprecise, they don't yield results that are going to be proper for what you're going to want to study. It also generates processes that shouldn't happen if you update it synchronously, meaning that since it's the discrete time, you skip the time for an entire time step. You can have a node that's connected to another node. One is infected, another one is recovered. And after one step of time, the infected the one that was susceptible, then the first one healed. But if you update them at the same time, you can be mixing stuff. Maybe what was supposed to happen was the first one healed and then couldn't spread anymore to the second guy. But if you update it discretely, in discrete time, you start having these events that shouldn't be occurring. That's a don't. The recommendation is to use continuous time. And a great algorithm for continuous time Poisson processes is the Gillespie algorithm. This is a paper by a few people from Universidade Federal de Viçosa, 2 professors, that they discuss optimizations for the Gillespie algorithm on pairwise contagion dynamics. And what I'm going to talk to you about now is generalizing the Gillespie algorithm in optimized versions for complex contagion or for higher order contagion. Okay, so hyperedges of second order, third order, huge orders, and so on. Let me just mention how the original Gillespie algorithm is. It's something like this. If you have this state here, this hypernetwork, this hypergraph, some nodes are infected, the 3, 4 is infected, and all the other ones are susceptible, they're going to be spreading the infection to all the susceptible nodes with rate of beta 1 for pairwise infections, beta 2 for second order infections. Then you have to build a list of all possible processes. This is for the Gillespie algorithm. You then pick what process is going to happen. Let's say, for example, I pick this node 4 to heal. I need to pick them proportional to their rates, okay? And then I update the list of all the events that can now happen after I cause this to change. You update the time following a logarithm of a random number. That's because the time step distribution is an exponential, so you have to use a logarithm of a random number generated between 0 and 1. This turns the distribution of time step to be an exponential as well. And there you have it. This is, in essence, the Gillespie algorithm. Build the lists, choose a process, update the time, then you build the list again. This list building and updating is costly. It's very costly. If you have many, many processes, you have to all the time go through the list, see what processes can happen, see what processes can't happen anymore, and keep updating it. So this is costly computationally. So what we do is we use an optimization that uses of phantom processes. I'll explain it to you a little bit more. We tried several optimizations, but I'm just going to have time to explain only one of them here for you guys. This is what we call a node-based optimized Gillespie algorithm, or NBOGA in short. What we do is, instead of building a list of all possible processes, we only build a list of quiescent agents, meaning agents that can get infected, agents that are in contact with an active hyperedge, okay? This is a simpler list. In the case for the drawing I made, there are only 2 that can be infected, nodes I and J. Then I'm going to pick what event will happen based on a few probabilities of healing. Each node will heal with a rate alpha and with a probability of infection. But the thing is, since my list is only of nodes that can get infected, I don't have the precise information stored of which hyperedges are active and the proper rates of them. So what we do is that we overestimate the infection rates of each node. That's not exactly correct, but it's a sacrifice that we made to create a list and update our list that is simpler. Okay, so I overestimate that every node is getting infected by all of its hyperedges, given by this number, k times beta. Beta is the spreading rate, k it's the degree, the generalized degree. Then, okay, I picked that node, but the key factor here is that I'll only infect it with a probability given by its actual infecting rate divided by its maximum infection rate. So If this probability is met, okay, I infect it. If it's not, nothing happens. This is what we call a phantom process. Then all the processes that will occur are only processes that are allowed to occur, nodes to be infected by proper happenable infections. And since I overestimated the rate here, when I come here and I forbid some processes to occur, I only contribute to a time step, the algorithm becomes exact, okay? It's a little bit complicated, but I do have the references you can check. And the point is, we tested for several types of networks. We tested for a homogeneous hypergraph. We tested for a simplicial complex. We tested for a power law, degree, and order distributed network. And we tested for a hyperblob. I believe this is a term coined by Gillespie, which is a hyper network that has a huge hyperedge that connects everyone at the same time. This is to test different types of networks to see if the algorithms are good. GA and GA plus are the common Gillespie algorithms, one the most basic possible, another one with few optimizations, and BOGA is the best one that we made. Just saying numbers is a little bit difficult, so I'm going to skip to a few results. This is first and foremost the GA, the normal GA scales. The CPU time scales with the system size squared, but the optimization scales with the system size only linearly. So it's better. It's much more efficient. To put it in perspective of hours and days, the basic GA and GA plus, they take 6 days to 4 hours to simulate a network of 32,000 nodes, which is a medium-sized network, okay? But the optimization takes that to 4 minutes. It's a reduction of around 99.99%. So yeah, and if you keep growing the size, it keeps getting better. Even in extreme cases like the hyperblob, the optimization goes from around 67 years for the basic GA, or 7 days to the optimized but very difficult to implement version, to 4 hours with our proposed optimization. We also tested it for some real networks. The event node events go off DBPL. The networks are here in the XGI library. This is the reference. And we saw that they are huge networks, and we saw that for the optimizations, we can get up to 12,900 time steps with the optimizations, whereas without the optimizations, you just can't work with them. Yeah, those are the aspects of the computer we ran the tests in, and well, that's about it. The conclusion: it's a methodological. I'm sorry if it was too much methodological to fewer details, but the idea is that the algorithm, it's important. Otherwise, we can't really work with networks that are too big. And we are interested in big networks because real systems are huge. So how are we going to simulate a contagion in a network of 100 nodes, since most contagions are of the order of cities, countries, and so on? So this is important. The work isn't completely published yet, but we do have some material here you can access. And well, that's about it.
Thank you. Thank you very much. We have time for 1 or 2 quick questions. Anyone who will be first? No? There was?
How times are changing. When we were young, we had presentations. We showed the first page of our paper. You show the QR code. So one says, this is a paper. Okay, now it seems like a very strange pattern. But then when you have to...
It's a modern... If there are no questions, I have one really quick. Does it parallelize?
It parallelizes.
So you don't have much inter-core or inter-node communication?
Yeah, well, we do, but it does parallelize us a little bit. We are not talking about parallelization or other things like...
That's my question, in fact. If you had talked about it, I would already know it.
Yeah, but the idea is that it does parallelize. We didn't focus it so much because we wanted to focus on the phantom processes. But like binary trees and other methods, they all work. They all can make it even better. We tested it. They all can make it even better, but the main point is that without it, it's already much better, but it paralyzes, yes.
Okay, well, thank you very much then, and we get ready for the next speaker.